Hello, my name's Professor Will Brown and I'm talking on behalf of my colleagues Dr. Yi Lu and Professor Bing Sui on a comparison of rule compaction algorithms for Michigan-style learning classifier systems. And this hot off the press paper is based on our journal that was published in Transactions on Evolutionary Learning and Optimization, otherwise known as TELO, which is an excellent publication venue for evolutionary computation techniques. It's thoroughly peer-reviewed, often with code available to support the work, and TELO is great because it doesn't have a page limitation, so you can really dig into the details. So today's talk is really just about an overview and the main points of our work. And to start off with the main points of the work, our contributions is looking at learning classifier systems, which are a 40-year-old technique that produce transparent rules, which are becoming more and more important in the age of explainable AI. And it's looking at how we compact populations of these rules to a manageable size so that we can then look at how the rules encapsulate the knowledge that we discover. We look at innovative compaction strategies and we look at the optimal format to present the knowledge discovered. One of the main reasons why existing compaction algorithms fail is the overlapping rule issue. And I'll illustrate this using the simple 4-bit majority on problem. And this problem gets a lot more complicated. It's a useful example. So we have the input bit 0000, and if the number of bits are in the majority 0, we put a 0. If it's majority of 1, we put a 1. And we want to get the classifier system to learn these details. And it does this by creating rules where you have the condition 00, don't care, as illustrated by the hash symbol, and then class 0. And these are examples of correct maximally general rules of action 0. But with evolutionary computation, occasionally we try rules that aren't as correct. And so we have overgeneral rules of action 1, and we also have overgeneral rules of action 0. And the idea of compaction is to only keep the correct rules and get rid of the rules that are overly general, whether they are correct or incorrect in their action. And to do this, the traditional ways look at what's important for the training set, and they look at both the training accuracy and the covering ability. But what we're interested in is whether or not the rules are subsumable and that they are correct. And we look at both the optimal set and the natural solution, which I'll describe shortly. And our techniques, Razor Cluster Razor, RCR, we've got 3 different versions depending on the type of problem we're trying to solve. And so the optimal solution O, as defined by Butts and Kovacs, refers to a single model that ensures there are no overlapping rules. And that can be really tricky in certain problem domains. Whereas what we say is actually we want a natural solution that contains all the patterns, and we believe this is beneficial. And so for the natural solution, we have all the possible rules. And you can see some of the blue rules are very different to the green rules, whereas Kovacs' and Butts' solution only looks at a subset of the rules. And we think we can gain more information by looking at the natural solution. And the trick we play is that we keep multiple populations. And what we found was that if you have multiple populations, the correct rules, or the natural solution, discovered time and time again. Whereas the incorrect rules, the ones we want to throw away, they vary each time we have a new population. So by looking across multiple populations, we can work out what is consistent, e.g. the correct natural solution we are after, and what is inconsistent, e.g. the incorrect overgeneral overlapping rules, and we can throw those away. And what's nice is we can then visualize these patterns. So if we have a single rule going down here, we can see if the bit is 00 and the second bit is 1, and this is for the multiplexer problem, we have action 1. And we can do some statistics and create the visualization here, which shows us visually the patterns in the data. And if we were to look at the natural solution for the 6-bit multiplexer problem, it highlights the importance of the address bits because they're always specified. But the data bits, which actually tell us what the action is, the bit that we care about in the output of our classifier, they're less well represented. Whereas in the natural solution, we find that the data bits, the bits that tell us what's going on, are really, really prominent. And we can do this for other problem domains. And we find really interesting patterns. For the carry problem, it clearly identifies that the first 3 bits and the last 3 bits are very important to add these together to find out whether the bit should carry or not. For the majority on problem, as we start to increase the size of the problem domain, we find a really interesting pattern. When it's an even number of bits, there's actually an imbalance between the 0 recommendations and the 1 recommendations, or the predictions. Where it's an odd number, they're exactly the same. And that's not obvious. So by using these compaction algorithms, we see hidden patterns in the data. Complex problems that require lots of different generalization levels, we perform at 100%, whereas the previous techniques have a tendency to remove 1 or 2 good rules, and that reduces their performance accuracy. For the majority on problems, the really large scale ones, where there's, say, the majority on 10-bit or the majority on 11-bit problem, again, RCR3, because it can handle the problem of overlapping rules where you might have only 1 in 124 instances being overlapping, it gets complete accuracy. And looking at this second row, that tells you it produces 924 rules that have to interact correctly in order to get the right answer. It also works for real problems, and there's more detail about this in the paper itself. And so to conclude, with these multiple model compaction algorithms, where you take the consensus over a number of populations, really help compaction algorithms scale to large scale problems and really improve the accuracy of our systems. And the natural solution reveals the nature of the explored training set. Thank you so much for your attention.